All right, let's jump right into this explainer and unpack the hidden physics behind product safety, specifically this really dangerous phenomenon known as electrical tracking. Look, if you're an engineer or a product designer, wrapping your head around this concept is absolutely crucial to make sure your devices don't just catastrophically fail out in the field. Throughout this explainer, we're going to lean heavily on the comprehensive tracking test expertise over at Ormity, and we'll look at how they evaluate materials for everything from your everyday household appliances right up to high-voltage electric vehicle infrastructure.
So here's our roadmap for this explainer. We'll start with the threat of tracking, then define the testing standards, and compare IEC 60112 and 60587. After that, we'll go inside the actual tracking test, talk about high-voltage testing safety, and finally wrap up with global compliance and calibration.
Section 1. The threat of tracking. Let's start with the root of the problem and see exactly what it is we're dealing with here. Have you ever wondered why perfectly good, solid hardware suddenly fails or, worse, catches fire after just being exposed to seemingly harmless dust and moisture? You know the drill. You test your PCBs in a pristine, clean lab, and they work flawlessly. But you drop that exact same board into a humid, dusty environment for a few years, and bam! Suddenly you've got a catastrophic failure on your hands.
Well, tracking is this highly destructive, invisible surface phenomenon where environmental contamination essentially creates a conductive track across what's supposed to be a completely safe insulator. When you have two conducting terminals sitting at a high voltage and the insulator right between them gets contaminated by moisture, maybe some thermal cycling, or just everyday dust, tiny, minute leakage currents start to flow. Over time, these currents literally carbonize the surface of the insulator. It turns a non-conductor right into a live conductor.
The hardware enthusiasts over at Hackaday hit the nail on the head when they said tracking is often the real culprit behind that dreaded magic smoke. You know the feeling, right? It's that awful moment when your prototype just fizzles, smokes, and dies. But hey, in a mass-produced consumer product, magic smoke isn't just an annoyance. It is a severe, massive liability.
And the real danger, the absolute worst-case scenario here, is when that tracking current sits just slightly lower than your fuse rating. The power doesn't cut off. Instead, it leads directly to a severe fire hazard. The appliance just keeps drawing power through that newly formed carbon path, generating immense heat. Because the current isn't quite high enough to trip the breaker or blow the fuse, the material literally just burns.
All right, moving into Section 2, defining the testing standards. What's really fascinating here is how the global engineering community tackles this dangerous problem through incredibly rigorous, standardized testing.
Major organizations, we're talking the IEC, ASTM, and UL, have developed these incredibly strict standardized procedures so we can accurately evaluate and, more importantly, compare different insulating materials. You literally cannot sell an electrical product on the global market without explicitly proving it can resist tracking. That's why securing these regulatory marks is absolutely vital.
Now, the main standards you're going to run into are IEC 61112 for your standard low-voltage tracking up to 600 volts. So that covers your typical PCBs and everyday household appliances. Then, way on the other end of the spectrum, we've got IEC 6587. This one is for much more severe, high-voltage ambient conditions, which is absolutely critical for modern applications like electric vehicle infrastructure and heavy-duty power grids.
On to Section 3. Comparing IEC 6112 and 6587. Let's see how this testing scales up, because these two IEC standards represent fundamentally different stress levels. They are absolutely not interchangeable. Honestly, understanding the difference between them is the key to specifying the right test for your product.
Okay, the crucial point here is this direct comparison. IEC 61112 evaluates materials horizontally using intermittent drops of a contaminant and platinum electrodes, testing up to 600 volts. On the flip side, IEC 6057 blasts an inclined plane set at a 45-degree angle with a continuous flowing film of contaminant and stainless steel electrodes, and that one reaches from 1 kilovolt all the way up to a staggering 6.0 kilovolts.
Basically, what this means is IEC 66112 is simulating light indoor pollution to find out exactly when a conductive path forms. IEC 6057, however, mimics really severe outdoor conditions where sustained arcing literally erodes the material. So if you're building an EV charging station or, say, outdoor high-voltage network equipment, the 6057 test isn't just checking for a tracking path. It is actively ensuring your material won't physically disintegrate under sustained electrical stress.
Okay, Section 4, inside the tracking test.
Let's get a look inside the actual test apparatus itself to see how the Comparative Tracking Index, or CTI, is measured. This is where high-precision engineering really comes into play.
Right inside the chamber, you'll find two pure platinum electrodes resting exactly 4 millimeters apart on a 3 millimeter thick insulating sample, and they press down with exactly 1 Newton of force. The precision here is paramount. Seriously, even a fraction of a millimeter difference in that gap could completely invalidate the entire test result. The test itself is this meticulous process. You apply the base voltage, then you drop a very specific 0.1% ammonium chloride electrolyte exactly every 30 seconds. Then you step up the voltage in 25-volt increments until the material finally fails. And those 30-second intervals, they're designed to simulate years of environmental dew and condensation hitting the board, just sped up in real time.
To pull this off, the test machines use incredibly precise digital drop counters and voltmeters to monitor everything. That's because the CTI value is specifically defined as the highest voltage the material can withstand for exactly 50 drops without forming a short circuit. Every single drop is carefully calibrated for volume to ensure completely identical stress on every test sample. Then, based on that final voltage, the material gets assigned a performance level category, or PLC. A rating of PLC 0 is the absolute best, meaning it withstood the highest voltages, while PLC 5 is the absolute lowest. Engineers rely heavily on these PLC ratings to select the right plastics for terminal blocks, switch housings, and internal components to guarantee the safety of the end user.
Section 5. High Voltage Testing Safety. As we transition into talking about actually operating these machines, we urgently need to address the human element, operator safety. When we test up to 600 volts or even up to 6 kilovolts for the EV standards, we are dealing with some very serious, very lethal power. Like I said, high-voltage testing involves lethal voltages. No way around it. In many laboratory setups, safety protocols are absolute, non-negotiable requirements that demand heavy personal protective gear to prevent fatal shocks or exposure to toxic fumes. Now, standard industry protocols will tell you to wear insulating gloves, mark out hazardous zones, and basically treat the machine like a live wire. But, and this is what's incredibly impressive about Ormity's specific testing apparatus, they actually engineer the danger right out of the process. Ormity secures their cabinets with fail-safe interlocks. If that door opens, the power instantly dies. Plus, they enclose the entire testing area behind a premium 6mm polycarbonate front cover. And it's really crucial to note, that is impact-resistant polycarbonate, explicitly not your standard fragile acrylic. Because of these robust built-in safety features, operating an Ormity tester is fundamentally safe. The machine literally does the heavy lifting to protect you. So while standard PPE is always a fantastic habit, with this setup it effectively becomes just a recommended bonus rather than your only line of defense against lethal voltage.
Finally, Section 6, Global Compliance and Calibration. At the end of the day, ensuring safety and data accuracy requires strict calibration of these high-voltage testers. Because, let's face it, even the safest machine in the world is useless if its voltage output drifts over time.
Calibration is a highly systematic process. It involves rigorous visual inspections and cross-referencing the output voltages against a highly trusted reference source. This prevents measurement drift that could dangerously compromise the product's safety rating. Think about it. A machine that outputs 580 volts when it says it's outputting 600 volts is going to pass a material that should actually fail, and that creates a massive, completely avoidable liability.
So, as we wrap up this explainer, I want to leave you with a question to really think about. Are your designs truly safeguarded against the invisible threat of magic smoke? And is your lab actually utilizing equipment that treats these lethal tests with the precision and the built-in safety they demand? Tracking might be an invisible threat, but with the right standards and properly engineered testing equipment, it's a threat you can completely eliminate.